SwayamPrabha. Digital India. Educated India.
Welcome to lectures 3 and 4 of week 8. In the last lectures, which was really consolidated lectures 1 and 2 of week 8, what we studied in detail was the derivation of the governing equations of a concentric tube resonator, a two duct interacting system, and we developed or set up the equations in which we can sort of solve the extend inlet and outlet a concentric tube resonator with extensions at the inlet and outlet, and we were just about to solve it. Okay, we basically got it in the form. Let me write it: week 8 and lectures 3 and 4 of this. So, basically what we studied or we just about to solve was this guy, this muffler configuration, which is quite famous, quite popular because of its low pressure, low back pressure or minimal pressure drop across its across the length, across the point 1 and 2, the inlet and outlet points. And here this part is your perforated section. So what does it really look like? What I have always been insisting, that it guides the flow, does not allow the flow to freely expand, it allows the waves to interact with the annular cavity and by here in the neck extensions. Okay. So, basically what it is doing is that here we have a sort of a pipe. So, this is perforates. So, what I am going to do now is that show you some nice photographs of the perforates, and before we even attempt to solve this, we have to overcome an important hurdle, and that is the perforate impedance, what we call, if we call this as region 1 and we call this as region 2. So, this is P1 minus P2 divided by rho naught C naught u star, which is the radial velocity, which is zeta. So, zeta, this has been a subject matter of several investigations since almost 40-50 years. In this course, to be very honest, it is almost impossible to cover all of them, but in fact, it is also difficult to give you a very proper chronological historical account of the development of such equations, of such expressions for this guy. But what I am going to do is that maybe talk about 3 or 4 of the important expressions used by different group of researchers worldwide. So, let us have a look at, before actually we begin to analyze the transmission loss in a MATLAB code, do some kind of parametric study of this CTR with extensions, CTRs with extensions. What we could do is that very briefly review the different perforated impedance that has been developed and used. So, for that, although I can write it down here on the screen, a better way would also be to have a look at the published literature. So, I have fortunately have got some theses and PDF files and different research articles which talk about different perforate impedance. So, let me show you a few of them. So, this is the thesis by Klaus Lahiri, who did some work on the acoustic performance of bias flow liners in gas turbine combustors. So, it was very good thesis on review of different perforate impedances used, and especially in context of liners for gas turbine engines. So, I need to show you some photographs of the exaggerated view of the nice perforated liner that is used in such things. So, here we see cylindrical pipe, and a part of that has array of small holes. So, these are basically what constitutes the perforates. So, the waves can go through them. This region where my mouse is pointing, that is probably the area through which this perforated section allows the waves to go and interact with the annular cavity where I am pointing. Now, this is these shapes can be, they are also known as orifices. They are basically small holes in kind of thin bent pipes or something like that. So, they need not be necessarily of circular shape, they can be of a number of shapes. So, they are called orifices, and as he mentions, orifice cross section shape is given by a cut through a plane normal to the direction of the orifice. So, a lot of them has been studied, like some of them are circular shape, elliptical, square and all that. So, he has drawn some nice schematic views of different orifices shape or the shape of holes essentially drilled through pipes, and each of them have different acoustic properties. That is, the shape of that definitely affects the perforate impedance. So, and another interesting thing is that it is not just the shape of the holes, the manner in which they are cut. For that, I probably have to go back to the presentation for just a bit, to the slides I mean, and what I am trying to say is that if we draw an exaggerated view of this, there could be something like this, something like this, or really parallelepiped kind of a thing. They are all arrays. So, wave and this is yet, so this is like a very small thickness, maybe about 2 mm or maybe 2 to 3 mm. This is a solid section, and the waves really go through them and interact here. Similarly here. Okay. So, let us get to the presentation of Claus, who has shown some nice cool figures. So, these are the different orifices, edge shapes, but what I was talking about now is that an overview of the orifice profile shapes. That is basically, what has happened is that you can see this is really an extended section like this, and there are holes drilled through, conical holes or maybe straight holes, and this is really cylindrical in shape, or this is conical frustum of a cone or of a sharp edge bevel or something like that, or inclined. It is like a cylinder kind of tilted in one direction. So, there are different ways in which the orifices can be cut through pipes of kind of small thickness, maybe 3 mm or 2 mm, 4 mm, something like that. So, now all this will greatly affect the perforate impedance, that is P1. So, suppose this is your section P1, this is P2. So, P1 minus P2 divided by the rho naught C naught into u star, which is the radial velocity, that is velocity in the direction that I am pointing. So, all these geometries or profiles have been sort of studied in the literature. And another important thing that one needs to sort of know here before we actually, I mean, these things one must know before we present the expressions for perforate impedance, because there will be a number of symbols. So, it is good to know beforehand what these numbers or symbols would mean. So, these holes can be aligned in different manners. They can be arranged in a square kind of a pattern, like something like this. So, basically what has happened is that suppose you unbend the pipe, or this is the development view, and you have holes of say circular shape drilled at regular intervals 1, 2, 3, 4 like this at uniform center to center distance along the circumference as well as along the this thing, because you can bend the pipe like here. So, this will become your circumference, and this will be the radial axial section. Similarly, you can have a rectangular thing that is basically have lesser holes in the circumferential direction if you bend it like this, and more number of holes along the axis, or vice versa. Then you have a staggered thing. Basically, staggered is like maybe something like having one hole in the center of 2 rows on the diagonal joining the 2 holes, something like this, where I am pointing, with different parameters, or non-uniform, completely random holes, that kind of a thing. So, basically the reason that it affects the perforate impedance, because it decides the porosity. So, that is basically your ratio, how much permeable the surface is, because remember we are modeling this by an impedance. It is like saying that the surface or the perforated part is a permeable surface. It allows waves to pass, but with a certain resistance or impedance, some opposition. So, that is what we are trying to model. Now, so one parameter that obviously becomes very important here is the porosity, that is basically the ratio of the total cross circumferential area, and what is the fraction of the circumferential area that is open. So, that is obviously given by the number of holes. So, basically the total open area divided by your overall circumferential area, that is your open area ratio, which is highly related to the porosity. So, what I would suggest now is that let us briefly review the expressions that have been developed for this thing. So, there is lot of literature and at times it can be sort of really overwhelming. So, to make things very simple, because this really is a first course or a fundamental course on muffler acoustics. So, I would stick to a very simple kind of presentation. So, first things first, so this is an extract from the textbook by Munjal, in which this basically perforate impedance expression for a cross flow is given. Then there is also expression for the case when there is no mean flow, that is a stationary medium. So, this is what it is. Let me sort of write it down on the slide. So, what we really have here is zeta for a cross flow. So, remember cross flow was something like this. So, you have your overlapping sections, say, and the flow was coming and it was forced to go like this, enter the cavity here, and then maybe sort of it is going here. So, it was something like this kind of a muffler. Okay. So, we will worry about that somewhat later, something like this. The flow has to necessarily cross from one perforated pipe through another one, perhaps in a overlapping section, and that is why this zeta for this cross flow configuration becomes important. Cross flow. Cross flow basically let me tell you, I will also obviously discuss this at a later thing when I discuss about the relevant maths behind this. But one thing about cross flow elements is that they have slightly better attenuation performance than simple grazing flow muffler configurations, but at the expense of higher back pressure. So, that is one thing you need to keep in mind. It is not like it can be used everywhere just because the attenuation performance is good. There are other constraints we also need to be mindful of. So, let us say zeta is your impedance here. So, P 1 minus P 2, assuming this is duct 1, duct 2 and so on, is your rho naught. So, flow has to necessarily traverse to this. It is not like the flow can just graze the surface, what we saw for this thing. In this, the flow can simply go like this straight with, and only the waves interact. The flow does not have to go through this, although there will be some non-zero flow, but we can sort of ignore it for most practical purposes. The flow, mean flow just goes like this, there will be no flow through the perforates, but in this case the flow has to go, because otherwise how it will go outside, go through the outlet. This is your outlet pipe, this is your inlet pipe. Now, for this guy we have 0.514 D1 M, where M is your Mach number, M naught you can say, and L, and I will talk about what L means. L is the length of the perforate, sigma is the porosity I was talking about, and plus J times 0.95 K naught T is the thickness of the perforated thing. So, remember T thickness means this guy is your thickness. So, T plus 0.75 diameter dH, and this entire thing is divided by sigma. This entire thing is sort of divided by sigma. So, this was for the cross flow configuration, and from where did we get this expression? Which research article proposed this this thing? So, it was given in Sullivan's paper, J.W. Sullivan, a long time back in JASA, a Journal of Acoustical Society of America. J. Sullivan published this formula, or this proposed this thing in JASA, Acoustical Society of America, in 1979. So, then for the stationary medium, in the same researcher proposed another expression for zeta, which is your 6 into 10 to the power minus 3. So, J K naught and T plus 0.75 dH an entire thing is divided by your sigma. Okay. One thing that is important in perforates, and we will soon see, is that this perforate impedance expression is complex. It is of the form A plus IB, resistive part or dissipative part and reactive part, or something that does not dissipate energy. So, now in case of what this expression really tells you, this is the expression for a stationary medium. So, when you have a stationary medium, you do not really have the concept of a cross flow. So, basically it is just like a simple perforated pipe without any mean flow. So, 6 into 10 to the power minus 3, this quantity is very small compared to at least this thing, and this thing particularly increases with frequency because k naught will increase. So, reactive part will increase. The point I am trying to make is that in the absence of mean flow, that is for a stationary medium considered, we do not really have the resistive part is basically very small, or there is no dissipation. So, one reason perforates do well is because they introduce additional damping into the system. They are like they are small viscous losses. So, all these holes that you had just seen, the array of holes that you have seen maybe in like this guy Lahiri gives you very good, this researcher gives you very good schematics. So, they are small holes, and this is the orifice cross section what he has really given. So, basically what I am saying is that when the waves are forced to go through these small holes, viscous losses become very important here. So, one hole will not do anything, it is only a cumulative action of small effects of each holes that really adds up and give you the overall effect in terms of some non-zero resistive part. So, but for a stationary medium, well, it is not very significant, it is only the mean flow when there is a non-zero mean flow, even for a grazing flow. So, all this thing that you saw, or this expression was for a cross flow, also known as bias flow. So, flow really has to go through the pipes. In the stationary medium, there is no concept of bias flow, but then there is thing like perforates with grazing flow. So, another group of researchers sometime back, they proposed a formula for perforates with grazing flow, and that was, let me write down the expression and we can sort of verify also from the book. It is 7.337 in 10 to the power minus 3. This expression was published by Munjal and M.N. Rao and Munjal. So, this I am sort of writing it down. We might use one of them for our MATLAB demonstration for evaluating the transmission loss. So, here we get this kind of a thing, 1 plus 51 T and 1 plus 204 T H and F. So, this becomes a bit messy. Let me just go directly to the book by Munjal, where these expressions are given. For the cross flow, D1 is obviously the diameter of the perforated pipe, and M is the mean flow Mach number, M or M naught, whatever you want to say. Sigma is the porosity. Now, porosity varies between anywhere between 5% or typically 7% to about 28 to 30%. So, 30% porosity means it is highly porous. So, it is acoustically transparent, as though waves can go through one pipe, the inner pipe to the annular section without without much obstruction. So, 30% porosity means it is nearly acoustically transparent, and as though acoustically speaking the pipe, the perforated bridge does not exist. So, one clever way, what engineering trick what people do is that if they want to do maintain some good aerodynamic performance and just get rid of the flow induced noise due to the flow expansion, they use a highly perforated section, 30% porosity and so that the waves are allowed to go through, allowed to pass through very easily, but at the same time acoustically the performance will be very similar to that of a extend inlet and outlet muffler. So, it would not sort of affect much acoustically speaking, but it definitely has a big very good influence or on reducing or kind of eliminating the separation noise that would otherwise occur. So, F is the frequency, like I was saying, T thickness of the perforated pipe, and dH is the hole diameter. So, this T is the thickness, and 2r or dh is the hole diameter. So, what about this expression? This was the expression given in Munjal, which I just sort of copied down on the presentation. So, m here is, basically the symbols are the same, and these were obtained through a large number of experiments, and this paper was published by these researchers, perforates with grazing flow, a long time back. Again, these are all historical expressions which have been used. So, I will talk about that, but this was published in 1986, experimental evaluation of impedance of perforates with grazing flow, published in Journal of Sound and Vibration. So, ever since that, a large number of papers have been published, and in separate investigations were reported on the perforate impedance things. So, the one paper is by the group in Egypt and in Sweden by Elnady and Abom. So, that paper I can just show a glimpse of that thing. It is already in this book, I believe the expressions are there. So, just bear with me for a minute. So, another impedance expression which has been used quite popularly since the last several years is the one by Elnady and others. So, that expression is given, has been used in several investigations and takes into account both the mean grazing flow and the mean bias flow. And so, this is the expression that is here. So, this zeta is given by nu plus j times chi. So, this nu is basically what they have done is a sum total of 4 different parts, and let me get to the paper which was published in the this work appeared in the Journal of Vibration and Acoustics, ASME journal, American Society of Mechanical Engineers, in I guess sometime in 2010. So, what they have done, this expression what is given in the book on ducts and mufflers by Munjal is adopted from the paper here, where they basically what they did was that basically it was given by modeling perforates as a system of 2 port elements, and what they said was that the grazing and bias flow impedance were calculated according to a previous work, and the resistance part or the resistive part of the impedance consists of 4 terms, like I was just about to mention. First is the viscous losses inside the hole. So, what is that? This is this part, viscous losses inside the hole. They are very small holes, about 2 or 3 mm in dia, and radiation resistance. In typical courses in fundamental of acoustics and all that, you consider piston oscillating in an infinite baffle. So, then you find out the radiation impedance or acoustic impedance right at the piston surface. So, all these formulas can now be, there might be a reason why we study all these things. So, there are a number of applications related to the simple models which are now useful. You see the utility of those models now. One is clearly the radiation resistance to the vibrating piston. So, you basically model the air column inside the orifice as a vibrating piston, and then the radiation impedance is given by 1 by sigma or porosity, and here J1 is the Bessel function of the first order and the first kind, ordinary Bessel function of the first order first kind, and again sigma is the porosity, mg is the grazing flow. So, basically the flow that just touches the perforates, does not really cross it, and mb is the flow that kind of goes through the duct. So, basically you can have kind of different this formula really combines the mean and grazing and bias flow. They can be perforated mufflers, very complicated ones like the one the photograph had shown in the beginning of this lecture, where you have a 4 duct interacting system, 3 perforated pipes and the big annular cavity which contains a big cylindrical elliptical cylindrical or circular cylindrical shell that contains the 3 perforated pipes. So, it is a multiple interacting duct problem and multi path propagation. So, in such a situation grazing and bias flow can occur simultaneously, and determination of these things are also not trivial. It is a research problem in itself. So, in such a situation this formula is applicable, but it is also applicable in other simplified situations like CTRs, where you just have grazing flow, or you can also have a cross flow in the other configuration that I just had briefly talked about. And now chi is your imaginary part or the inductive part, or it is also called reactance. So, now basically this is the reactance is assumed to be caused only by the mass plug, and any flow effects on the reactance are neglected. So, f mu dash is basically, these are all sort of functions. were derived through number of theoretical models, and these expressions, these constants are basically fitted to some experimental data by these researchers. So, this is one sort of one popular expression, and your sigma, which is your porosity. So, what is sigma? How do you determine porosity? And actually what is also, there is another thing, that what do you, let us also talk about different symbols here. CD is the coefficient of discharge, K is as usual the wave number, K or K naught, forcing frequency, and C is the sound speed, and nu is mu by rho naught, that is the kinematic viscosity, and nu dash is 2.17 times mu. So, there are number of things here. We just talked about this sigma, which is the porosity. So, what is, how do you define porosity? In fact, how do you, like, let us say, if you are given the job of fabricating this perforated tube, which was fabricated by us some time back. So, how do you define, like, it is clearly seen that this guy, where my mouse is pointing, this is much more porous than this one. So, porosity sigma is defined as the total area of the holes. So, let us say in all, like for example, if you go back to this figure, the total area of holes is really the area of one hole, let us say diameter is dh. So, pi dh square by 4, and nh is a number of total number of holes, okay, that you can have equal number of holes per ring, and they can be something like m number of rings and n number of holes in one ring, or you can have different configurations, like this is clearly something like a square kind of a configuration. You can have rectangular, you can have staggered. In the most generalized sense, if nh is the total number of holes and pi dh square by 4 is the total is the area of each hole, okay. So, this is the total area due to the all the perforated holes, okay. And what is the cross sectional, what is the cylindrical or curved surface area of the perforated pipe? It is not from this point to this point, it is from just from the extreme, like for example, just where the hole, the array ends, like this is the array where it ends, from this section until this section where this pipe is there, that is the perforated length. In this case, it is probably from the ring, the length, let us say from here, from this point all the way until this length. So, so basically the idea is, if capital D is your diameter of the perforated duct, so pi d into LP, pi d into LP will give you the curved surface area. It is like really like a rectangular when you when you do the development. So, pi d is the circumference, or 2 pi r naught or 2 pi d naught divided by LP. So, basically this is the porosity, and clearly if numerator is more, that is the total area covered by the holes is much more significantly large or substantial compared to the this curved surface area, then porosity is more. So, typically we do not have porosity greater than 0.3, it is always about less than 30%, and like I said, it is almost acoustically transparent, like as if the perforate did not exist, but mechanically it does, and it it does not make much sense to go less than 0.5, even 0.05 is less, it is quite small. So, typically we vary it from 0.08, 0.1 all the way until 0.28, 0.3, something like that. So, these are the typical values. There is also something like open area ratio. So, open area ratio is related to sigma, that is the total area of the covered by the perforated holes divided by the cross sectional area of the pipe. So, in place of this guy you would write pi d naught square by 4, so you can then simplify matters and get the things, but so open area ratio is important for getting the back pressure due to these things. We are not probably going to talk about that in this course, but just for knowledge sake I thought of mentioning OAR, open area ratio also. Anyhow, let us get back to the review, a very brief review of the perforated expressions that are available in the literature. So, this is this one, and then Lahiri, like I said, gives an excellent review of the different perforated impedance that is there in the literature. So, what we have to do is that look at the different expressions. So, impedance Z is equal to P by Q, or pressure by volume velocity. Typically, like it is mentioned, Lahiri also says impedance is resistive part plus I times the reactive part. Real part is resistance, imaginary part is the reactance. So, there are different models. The acoustic impedance can be written as sum of three quantities, R resistance or damping, and M is the mass inductance, and this C is the compliance. So, these are the lumped parameters. So, there are number of mathematical or theoretical models based on different researchers over different years. So, noticeably what is important is like there are few parameters like internal impedance of the orifice, as well as the mass end correction, that is due to radiation reactance I was talking about, resistance end correction, and a number of things. So, this is one formula where zeta is I k times this thing. So, here of course, the mean flow effects are not quite considered. This is the orifice interaction. There are number of formulas, one by Melling, zeta is equal to I k times sigma by a number of complicated functions, where these are the different things given in the work by Folk. So, it is pretty hard to review all of them right now, but just for the sake of knowledge, it is good to understand this, like this is a more comprehensive formula involving resistance as well. Then you have a grazing flow impedance models, and a large number of such models are there. So, the entire thesis is devoted to that. Now, I will just go through that. Maybe to the people who are interested, they can read it. For example, Betts model is this thing where there are some expressions one needs to understand that. So, basically I will kind of stop the review of this thing here, at least with the understanding that at least when the annular area is empty, that is there is no dissipative material in the lining, one needs to really consider an appropriate expression. For our cases, we will use most likely we are going to use the expression given by Elnady and others, and that is quite, like I said, there has been quite popularly used. And just for the sake of completeness, I must also mention that there are also other models available in the literature where the annular area. So, let us go back to the presentation. If this area is filled with an absorbent material like a rock wool, glass wool, then of course quite complicated expressions for the impedance of the perforate exist. So, here we consider bulk reaction. Maybe if we get time, we will consider this in the course. Bulk reaction models here, bulk reaction models, bulk reaction wave propagation, and here there is a regular wave propagation in the airway. But before the wave interacts or goes in this thing, it has to cross through the impedance through the perforated bridge. Okay. So, for that we need to develop suitable expressions. People have already done it. So, another, like I was mentioning here, this is an important configuration schematic of a line duct with annular air gap between the central airway, that is your this one central airway, and the absorptive material. This is like a hybrid kind of a muffler. You have a resonator or neck extensions at the inlet and outlet, plus the waves can also go through interact with the annular cavity. So, this it's like the best of both the worlds, because this dissipative things you will see, hopefully we will see in the later parts of the course. This is effective only at high frequencies. So, at low frequencies, the reactive parts can do their job by providing suitable attenuation, and at high frequencies the dissipative parts probably can take over. So, this is one result also only from the plane wave analysis, the ITM method, which is called the integrated transfer matrix method developed by Munjal and his group. So, it matches quite well for the configuration dimensions considered with the 3-dimensional results, but for larger mufflers we still have to use a 3D thing. But what I was trying to show you is this expression. Now, what does it do? It is a modified impedance expression. Now, notice the fact that here you have a very small real part 0.06, and here you have 0.375 dH. So, when YW and KW are the characteristic impedance and the wave propagation constant, wave number in the dissipative material, and K0, Y0 are the counterparts in air. So, when this is 1, so this becomes, when that is basically when you have YW and KW are equal to Y0 and K0 respectively, when the medium is air. So, this becomes 1. So, this is 2 and 0.375 will become 0.75 dH. So, you basically get back the medium expression for the case of a stationary medium in case of 0 mean flow and there is no dissipative material on the other side. There is on both sides of the perforate there is only air. That is one thing, and then there are other expressions also, there are lots of them, it is almost impossible to cover the entire thing, but and they have been obtained either through some theoretical models and validated by some impedance tube test, or by basically directly fitting some empirical formula to the experimental values. But and one such expression, this is a paper by Kirby published in JSV a long time back, where he basically considered this kind of a muffler configuration, a straight through muffler filled with dissipative material in the annular cavity, and again it is the same problem. One needs to find out the perforate impedance with backing on one side with the absorbent material. So, well, this paper is devoted to something else, but it is quite, it will be good if we can just have a it is a finite element development paper for analyzing these such configurations, but what we can the take home message from this particular thing is that to have a look at the perforate impedance expression. So, for the perforated pipe, the normalized impedance zeta is given by this thing, which is given in reference 5, zeta dash plus this thing, where f of sigma, that is given in the paper by Folk, and there are different expressions for f sigma, and zeta dash is also found out previously. Zeta dash is the orifice impedance measured in the absence of an absorbent material, and values of zeta dash were measured by Kirby and Cummins. And so, there are a number of such things where one uses the proper material, and all these constants that we see here, they are specific for a particular material. Okay. The point is that based on the type of muffler configuration that one is analyzing, so suitable thing can be found out, a suitable perforate impedance can be found out and used. So, for our cases, since in this we can possibly, in the next week we will be doing reactive mufflers without any dissipative thing, I think we will probably use the expression given by Elnady. So, let us now, I guess it is time now to get back to some muffler analysis using MATLAB and get back to the presentation. So, we already have got ddz of Bx is equal to Ax, we saw that, and x was a state variable for a two duct interacting system, something like this. Okay. We had such a system. Okay. What do we need to do now from here? We need to basically, we have P1 rho naught C naught U1 and P2 rho naught C naught U2. So, we need to do B inverse A and get the C matrix, was not it? We did P inverse A times B inverse A, and so ddz of x was this. So, this guy was your C matrix. Now, one thing that we realize that because of the particular rearrangement of the equations on the right hand side, we put the continuity equation first and momentum second and so on. So, it led to a different form of the B matrix. So, we kind of slightly rearrange that. Momentum equation is the first row now, continuity equation is the second row and so on. So, with this kind of a small rearrangement, it is easy to see that when m naught is 0, that is stationary medium, we get B as I, identity matrix, which is very obvious. Now, when m naught is not 0, then we need to invert that matrix, and that is what we are doing here. Okay. So, the point is now with this understanding that we have got this equation, we will sort of use the exponential matrix to get the finally the form that we talked about, that is your x is equal to state variable at x equal to 0 is equal to T matrix times x at L. We talked about this thing, where your T matrix is really your exponential m times minus CL. It just becomes all the more easy. Now, once we know your perforate length L, that is overlapping, perforate length L, and diameter of the perforate pipe and the annular cavity or just the cavity D2, and the suitable and the frequency at which we are solving the particular perforate model, we can sort of easily put in the expressions and go about doing that. So, we will now go to the MATLAB code where the code is already written, and I will explain the stuff to you and then run some codes and run the codes with different extension lengths LA, LB and get different curves and see how do we reduce to the case of a concentric resonator, and we will talk about that in the next lecture. So, thanks for attending.